All right, well, this video is about learning about how to find end behavior asymptotes, as they are called. So throughout the week this week, we're going to be talking about different types of asymptotes. So, of course, depending on if you're watching this video at the beginning of the week, this will be a fairly new idea. For those of you watching it at the end of the week, we'll have kind of talked about asymptotes in class a little bit, but this will be more about what we call end behavior asymptotes. So the homework you had to do for this week, from last week, talked about end behavior. And so we know that normally when we talk about end behavior, we use limit notation to say, what the graph is doing as you head to infinity, to the left and the right. So what we want to talk about now is particularly what is the asymptote that the curve is headed along. So remember that an asymptote is just a line or another curve that the graph approaches but never touches. And so for the most part, up until now, you've only seen asymptotes that are vertical asymptotes. But they're actually also horizontal asymptotes. And as we're going to see today, there's also what we call a slant asymptote. And sometimes asymptotes can even be other shapes like parabolas and cubics and things like that. So we're going to see today how to find the equations of those other asymptotes. So recall from what we've done already this year that the end behavior of a rational function, right, is not a horizontal line when. So remember we had three cases, and so the case where we would not get a horizontal line is if the degree of the numerator is greater than the degree of the denominator. Right, so that's the case where we would end up with an end behavior that is not a line. So remember, if the top and the bottom are equal degree, then we would just have a horizontal line at whatever they simplify to. If the denominator has a greater degree, then it's always going to be a horizontal asymptote at y equals 0. And so now we're left with the kind of more tricky case, because depending on how much bigger the top degree is, that's what is going to determine our asymptote. So if we look here, right, if we use that comparison method that we talked about last week, right, as x goes to either positive or negative infinity, so as we pick things that are really, really big, either positive or negative, which term would dominate the numerator? So the thing that would dominate the numerator is, of course, the highest degree piece, so that would be 4x squared, right? Because if I start plugging in big numbers, that's going to take control. And on the bottom, as I go to negative or positive infinity, the thing that's going to take control would just be the x, right? So you think about if I pick a really big value for x, subtracting 1 is not really going to have an effect. So it would just be x, okay? So if that is true, then by looking at the leading terms of the numerator and denominator, it would appear as if the graph approaches the function. So if we took 4x squared over x, right, then that would just simplify to 4x. And so that is a good approximation, right? And that would certainly help us figure out the limit notation, because we know that 4x is just a line that does this. So we definitely know that, the limit of this function as we go to infinity would be infinity, right? So as I go to the right, it would go off to infinity. And then the limit of this function as I go to the left, it would go down to negative infinity, right? So we definitely can see what the end behavior is based on that approximation. However, let's see if that's truly the asymptote. So if I open up Desmos here, oops, oh, Desmos isn't open. Hang on a sec. There we go. So if I open up Desmos, thought I had it open already, but I guess not. And I just graphed that lovely equation. So the equation was 4x squared plus 6x plus 9. Having tech issues today. It's late. All right, so let me type this in here. So 4x, I'm going to put it in parentheses, squared, plus 6x plus 9. I'm going to close those parentheses, divided by x minus 1. Right. So if I look at that graph, let's move this over so we can see it better. Right, so it looks like that. Okay, so this is a really cool looking function. And so we thought that the asymptote might have been, or at least approximated, to 4x. So if I draw 4x in there, you can see that that's not really the asymptote, right? Because an asymptote should be a line that the other function runs along. So up there on the positive side, it kind of runs along it. But down here in the bottom quadrant, right, in quadrant 3 down there, you can see where it kind of cuts through and it just doesn't quite do the job. Now, if we were to zoom way out, right, as I go to infinity, then it kind of does look like the asymptote, right? And so it is a good approximation, which is why we're able to do that comparison method. But if we want to know the exact asymptote, this isn't going to quite cut it. So this is where our review of division comes in. Okay, so as you can see in part D, it says now graph them, right? And does it seem to approach the answer as we zoom out? And so, yeah, it does, right? I mean, if we zoom way out, it certainly looks good, but it's not quite the asymptote. So this is where we actually can use synthetic division or long division if needed to help us out. So if I come back up here to the function, right, the fraction bar means division, right? That's what that means. So if I go ahead and divide, and so thankfully I can do synthetic. So what goes on the shelf would be positive 1 since it's x minus 1. And then I would have a 4 and a 6 and a 9. So bring down the 4. 4 times 1 is 4. Add, I get 10. 10 times 1 is 10. Add, I get 19. So my power is going to drop. So if it was originally a quadratic, then that means that this is now 4x plus 10. And then I've got a remainder, right? So the remainder, though, remember, one way we can write this is that we say that the remainder still needed to be divided by x minus 1. And so if x, right, is headed to infinity, then that means that right here, this would be saying 19 divided by a really big number. And so what happens is that this part essentially drops out. Right? As I go to infinity, that part is completely negligible. And so this becomes what we call a slanted asymptote. So it's an asymptote, but it is a slanted line because it has a slope of 4x plus a 4x. Right? The slope is 4. So if we go back into Desmos here and we change our approximation to 4x plus 10, look at that, like a glove, just slides right in there, right? So you can see where that asymptote just fits right perfectly between the curves there. And so we now know that that is the exact asymptote that it's going to approach as we go to infinity. So that's pretty cool. So I always like asymptotes. They're pretty sweet. So there you go. So that is one of the reasons that we use long and synthetic division, is to help us figure that out. So we try one more here, right? So again, if I just use the comparison method, right, I would just be saying, well, I've got x cubed and I've got x, right? So the comparison method would say, well, x cubed over x is x squared. So that's a parabola, right? So if I just want to write the end behavior using limit notation, that's good enough. I know what the end behavior is now, right? So as I go to the left, it's going to go up. As I go to the right, it's going to go up. So the comparison method works great if all we want to know is what's it going to do. So we know it's going to go up, up. But if we actually want to know the equation of the asymptote, right, now we need to actually go through the division. So that's the difference, right? One is just asking for the general end behavior. The other wants the actual equation of that asymptote. So again, we say, well, That means negative 3 would go on the shelf. Since it's the opposite of the x plus 3, it's the root or the 0 of that. And then our coefficients would be a 1, a 5, 1, negative 12. Bring down the 1. 1 times negative 3 is negative 3. Add, I get 2. Multiply, I get negative 6. Add, I get negative 5. Multiply, I get 15. Add, I get 3, right? So that's my remainder, which again, for what we're doing, as I go to infinity, that remainder doesn't matter. And so if this was a cubic and I divided by x, then it's now going to be 1x squared plus 2x minus 5. And so we actually have a parabola that is my asymptote. So how cool is that, right? Little did you know that asymptotes could be parabolas. So an asymptote, again, is anything that the curve approaches, right? So it does not have to be a line. So I think that we should definitely look at this. So let's take a look. So if I come in here, we'll change this to x to the third plus 5x squared plus x minus 12, right? And then we'll come in here. And so let's just, for the comparison method again, like let's just look at what x squared looked like, right? And so if I do that, you can see, I mean, you know, it's almost like there's two parabolas there, right? But I suppose if I went way out to infinity, you don't really notice a difference, right? But now we know that it's actually x squared plus 2x minus 5. And so now, let me do this so we can see it better. Okay. So now you can see, wait a second here. X squared plus 2x. Doesn't quite look perfect to me. Normally it would look a little better than that. So that actually tells me I might have made a mistake. Did I type something in wrong there? Let's see. This is why graphing can always help us check our answer. X cubed plus 5x squared plus x minus 12. Oh, yeah. I forgot to change the denominator, didn't I? There we go. X plus 3. All right. Oh, yeah. That's much better. I was going to say that didn't look very good. Okay. Usually they're closer than that. So now let's come in here. Oh, yeah. Look at that. Like a glove. So you can see the green parabola is actually the asymptote, right? The original curve is that red curve there. And so if I take off the green, right, there's my graph. And so you can see where this graph actually looks like a parabola, but it's got this extra stuff going on, right? But when I sketch in the parabola there, I can see that as it went to infinity, it would have run right along that parabola. So that is pretty nifty. All right. So that was the correct answer. I just typed it in wrong. Okay. Let's do one more, right? And so again, if we use the comparison method here, right? So if I use the comparison method, I just look at the highest on the top and the bottom, right? So 2x cubed over 2x squared would actually just be x, right? So that tells me that as I go to negative infinity, it's going to go to negative infinity, right? Because x is just going to be a line that would look like this. And then the limit as I go to positive infinity would be infinity. So I've got the end behavior, right? That's what it's going to do, down to the left, up to the right. But if I want to know what that actual asymptote is, then this is, again, where I get to use division, and unfortunately, this is one where I'm going to have to use long division, right? So sometimes we do indeed have to use long division. Doesn't happen too often, but it does happen, right? So how many times does 2x squared go into 2x cubed, right? So that would be x times. So I left a little space there so I could put my 0x in, right? And I could actually put it out here as well then, okay? So I've got that little placeholder. So how many times if I do 2x cubed divided by 2x squared, right? I know that's x, so then I multiply down. So I'd have 2x cubed. X times 0 would be 0x squared. X times 1 is x. Subtract. So I'm going to have 3 minus 0, so 3x squared. And then this would be a negative x, right? Because 0 minus 1x. And then I bring down that 7. I do it all over again. So 2x squared goes into 3x squared. Right? So 3x squared over 2x squared would be 3 halves. Okay, fair enough. So 3 halves. Okay. Yep. And then 3 halves times 2 would be 3x squared. And then 3 halves times 0 would be 0. And then 3 halves times 1 would be 3 halves. And you may be thinking, oh my gosh, this is going to be so disgusting because I have fractions and stuff going on here. But here's the great thing. Everything else is just going to be a remainder down here, right? Negative x, right? And then 7 minus 3 halves would be 5 1/2. Right? But again, I can't divide 2x squared into that. This is my remainder, so I don't even care about that because as I go to infinity, this is what it's going to approach. So the great thing is we can always just ignore the remainder because we are just curious to know what that asymptote is going to be. So our asymptote is going to be y equals x plus 1.5. And so we could sketch that if we wanted just to double check and make sure we did it right. But I'll assume it's okay unless you find a mistake, and then you can get a donut point if I did do something wrong because it's late and I am ready for bed. All right. Have a good one. And so your task then is just on Canvas. You'll see there's a worksheet then, an assignment that asks you to find the end behavior asymptotes. Some of them are just horizontal lines, right? So that would just be like y equals 0 or y equals 2. And then some of them are like this that require you to do some division to actually find that asymptote. So good luck with that, and I will see you in class when I see you.